Hi all, today we are going to discuss about the inductor filter and we are going to prove the complete derivation for the inductor filter using inductor, how the output current waveform becomes nearly linear or how our output current waveform is improved. So the inductor filter is connected in series with a resistive load to decrease the ripples in the current waveform and to make it more smooth. Like for example, if I am taking the full wave bridge rectifier, which is used in most common for single phase, so I am conducting an inductor filter in series with my load. Let us assume my load is a pure resistive load. In the case of pure resistive load, if this inductor filter is not there, so your output voltage will be, during the positive half cycle, diode D1 and D2 are forward biased. So diode D1 and D2 will conduct. So your output voltage will be, this A comes to here and this B comes here, your output voltage will be equal to VAB. So your output voltage will be equal to VAB, and after half cycle then this diode D1 D2 get reverse biased because your A becomes negative and B become positive. So diode D3 and D4 are forward biased, they will start conducting. So during this time the voltage that comes will be equal to VBA, and here this is conducting due to diode D3 and D4. So now because it is a pure resistive load, the current, output current will be equal to output voltage, instantaneous output voltage by resistance. So your current waveform also resembles your output waveform. So it will have so much harmonic components. That means it is not smooth. So in order to smoothen out your output waveform like this, so what we do, we connect one inductor filter. So we are going to prove that by adding an inductor filter, your output waveform will become more smooth, and this will be your source voltage because for half cycle D1 D2 are conducting and for another half cycle D3 D4 are conducting. So now coming to your output voltage, your output voltage will be equal to V maximum sin omega t from 0 to omega t less than or equal to pi. That means from 0 to pi, this VAB is nothing but V maximum sin omega t. From pi to 2 pi, it is nothing but equal to this sine wave shifted by 180 degrees. So I can write it in the form V maximum sin omega t minus pi, or I can write it in another way. It is nothing but, because this is just 180 degrees opposite to VAB, because VBA is equal to minus VAB. Agree with me? So this I can write as minus V maximum sin omega t. So with these basics I am proceeding further. So we have already seen how to analyze the output waveform. That output waveform can be represented as a sum of the DC and AC components by using the Fourier series analysis. So in the Fourier series form, this output voltage, instantaneous output voltage, can be represented as a sum of A0 is the DC component, plus this remaining thing is the AC component, which can be represented from n is equal to 1 to infinity. N is the order of the harmonic. An cos n omega t plus sigma n is equal to 1 to infinity Bn sin n omega t. So where the value of this A0 is 1 by 2 pi integration from 0 to 2 pi. You have to take your whatever is the value of the, this is not Vs, this is equal to V0. So V0 d omega t. So this way you have to analyze, and now the value of An will be equal to 2 by 2 pi integration from 0 to 2 pi V0 cos n omega t d omega t. Instantaneous value you have to multiply with cos n omega t. Similar is the case, I can write my Bn will be equal to 2 by 2 pi integration from 0 to 2 pi V0 sin n omega t d omega t. Same thing, the output waveform I have represented here. This during from 0 to pi, I can write the equation as V maximum sin omega t, and from pi to 2 pi I can write as V maximum sin omega t minus pi shifted by 180 degrees, or omega t minus pi. This sin omega t minus pi is nothing but equal to minus sin omega t, right? So this I can write as minus V maximum sin omega t. So I am proceeding further. So DC component A0 will be equal to 1 by 2 pi. It is having two components, 0 to pi and pi to 2 pi. From 0 to pi it is V maximum sin omega t d omega t, and pi to 2 pi it is minus V maximum sin omega t. That is why minus I have taken outside. Integration from pi to 2 pi minus V maximum sin omega t d omega t. We know the integration of sin omega t is minus cos omega t. I have substituted the limits 0 to pi. Similarly here also it will be minus cos omega t. Limits are pi to 2 pi. So when you substitute the limits, you will get your answer as 2V maximum by pi. So we can tell that out of all the component, the DC component is 2V maximum by pi. You can observe it, the same value we got when we are calculating the DC component, when you are analyzing the bridge rectifier also. So now let us try to analyze the AN component. So AN again will be 2 by 2 pi, or simply I can write it as 1 by pi. Again the output is having two components, that is 0 to pi and pi to 2 pi. 0 to pi the output voltage is V maximum sin omega t. I have to multiply V naught with cos n omega t. So I have multiplied with cos n omega t d omega t, and from pi to 2 pi it is minus V maximum sin omega t into, I am again multiplying with cos n omega t d omega t. So this is of the form 2 sin A cos B. So this I can write of the form sin A plus B plus sin A minus B form. So this omega t is common in both the things. So this I can write as 1 omega t, this is n omega t. That's why A plus B I have written sin of 1 plus n times of omega t, or this is nothing but sin of omega t plus n omega t, plus sin of A minus B, sin of 1 minus n times of omega t d omega t divided by 2. That 2 I have taken outside, and this V maximum also I have taken outside. So this is from 0 to pi, and from pi to 2 pi it will be minus, remaining thing will be same. So this I am proceeding further. When you do the integration of sin omega t is nothing but minus cos of 1 plus n times of omega t divided by 1 plus n. This is what we get, minus. So the second component will be sin of 1 minus n omega t will be cos 1 minus n times of omega t divided by 1 minus n. So these limits are 0 to pi, and for the second one the limits are pi to 2 pi. As this minus sign is there, I can reverse my limits to compensate for this minus. So when I reverse my limits, it will be 2 pi to pi. So you have to substitute two things, 0 to pi and 2 pi to pi. So you will get the same answer. So when you are substituting it, you will get it as V maximum by 2 pi into 2 times of this value. So this 2 will cancel. This I can write as V maximum by pi into, I am separating the cosine component separate and remaining component separate. This will be 1 by 1 plus pi plus 1 by 1 minus n, 1 by 1 plus n plus 1 by 1 minus n, right? So when you are simplifying it, it becomes 1 minus n plus 1 minus n divided by 1 minus n square, 1 minus n square. So this will be equal to 1 plus n, right? So 1 plus n divided by 1 minus n square. So minus, so the remaining term cos A plus B. So this I can write as cos A cos B minus sin A sin B form. So in that form I have just expanded the things. Getting it? So now I am proceeding further. So this will be, when you simplify it, you will get in this form. So when you are simplifying further, you will get the equation in this form. 2V maximum by pi into 1 plus minus 1 whole to the power of n divided by 1 minus n square. Because how this minus 1 to the power of n came? Because we know that cos n pi is nothing but minus 1 whole to the power of n. Okay. Now calculating the value of this value, this is nothing but an. This an will be equal to 0 when n is equal to odd. When n is equal to odd, this becomes minus 1. 1 minus 1 will be equal to 0. Numerator becomes 0, so entire an becomes equal to 0. But this will violate for the case n is equal to 1. When n is equal to 1, you can see both numerator and denominator as becoming 0 by 0. 0 by 0 is indeterminate. So let us calculate it separately. Now coming to the even number, so when n is equal to even, this n1 become positive, this will become 2. So that's why we can write it as 4Vm by pi into 1 minus n square. As n is greater than 1, so I am reversing it, so minus sign will come here. Minus 4Vm by pi into n square minus 1. This is for n is equal to even. So I have already discussed this an will become indeterminate for n is equal to 1. So I am calculating it separately. A1 will be 1 by pi. Integration from 0 to pi, just substitute n is equal to 1. Cos n omega t is there. Substitute n is equal to 1. This become B max on sin omega t cos omega t minus integration from pi to 2 pi. So same thing will repeat here. So this is 2 sin A cos B. So this I can write as sin 2 omega t divided by 2. That 2 I have taken outside. V maximum also taken outside. This becomes V maximum by 2 pi. Integration from 0 to pi sin 2 omega t d omega t minus pi to 2 pi. Again same thing will repeat. So if you simplify it, you will get your answer as 0. So from this we can summarize that the value of an will be 0 for the case of odd number, and it will be equal to minus 4Vm by pi times of n square minus 1 for even number. Now let us calculate the value of Bn. So Bn will be equal to 1 by pi, integration from 0 to pi, V maximum sin omega t, we have to multiply with sin n omega t here, d omega t, and from pi to 2 pi it is minus V maximum sin omega t. So same thing will repeat here. So this I can write as 2 sin A sin B form. This is cos A minus B minus cos A plus B divided by 2. So that 2 I have taken outside, V maximum taken outside. This is cos A minus B, that means 1 minus n times of omega t, minus cos A plus B, that is 1 plus n times of omega t. Okay, same thing here with the minus sign. So this I have simplified, just done the integration and substituted the limits. When you substitute the limits, you will get this answer as 0. So we are getting the Bn is equal to 0 and An also only for even numbers it is non-zero, and DC component is 2V maximum by pi. So finally I can summarize my output voltage, I can write as 2V maximum by pi minus 4Vm by pi. This is only for even numbers, that's why n is equal to 2, 4, 6 etc. up to infinity cos n omega t divided by n square minus 1. So when you are expanding this, this contains the DC component and this contains the AC component, only even harmonics are there, 2, 4, 6 only these are there, minus 4Vm by 3 pi cos 2 omega t, minus 4Vm by 15 pi cos 4 omega t, like that it will come. So actually I want my output should have the pure DC component, but along with the DC component, AC component is also coming. That's why it is called as a ripple component or harmonic component. So we have seen that the average load voltage is nothing but the DC component. Out of this equation, DC component is 2V maximum by pi, and the load impedance for nth harmonic, because I have connected L also, so it is RL circuit is there now. For RL circuit, we know the impedance is equal to square root of R square plus XL square. So for nth, because omega is equal to 2 pi f, for nth harmonic that frequency becomes n times. So that's why I have written n omega L whole square. This depends on which order harmonic it is opposing. That means this impedance is offered for which particular harmonic component. Like for example, for DC component, n is equal to 0. So only resistance will be there. So now average output voltage or DC component of output voltage will be DC component of output voltage divided by impedance, DC component of the impedance. It is nothing but V0 divided by, when n is equal to 0, this becomes R. This is V0 by R, that is 2Vm by pi into R. This is my average load current. So along with this, AC components are there, or we can write in a generalized formula for I0 as that AC component divided by impedance. You agree with me? That means V0 divided by impedance. So DC value of the impedance will be only resistance. So it is 2V maximum by pi into R minus 4Vm by 3 pi. This will be equal to square root of R square plus, it is a second harmonic, 2 omega L whole square into cos 2 omega t minus theta 2. You can see here the current is having extra component along with the voltage. Voltage is 2 omega t only. Along with that theta 2 came, because the reason is because of R and X, the impedance is making some angle with respect to the voltage or the reference. So that's why this theta is a tan inverse of, for nth harmonic, this is n omega L divided by R. Xn is n omega L. So this indicates the angle by which I0 is lagging behind the V0n, because we know for the inductive load the current lags the voltage. That's why I have written minus theta 2. I hope this is clear to you. So now proceeding further, that I0 I can write as a sum of DC component plus AC component. That AC component is not required for me. That's why we can call it as a ripple current. Okay, so this is my ripple component. So we are analyzing the ripple component. So we can calculate the RMS value of this harmonic component of the current or ripple component of current will be, we have to remove this DC component, remaining component I have to calculate the RMS value, because we know the RMS value is nothing but peak value divided by root 2. Agree with me? So I can calculate my ripple component by square root of each component, each RMS value square we have to do. So first one is 4Vm by 3 pi. I have divided with root 2 to get the RMS value whole square into 1 divided by R square plus 2 omega L square. Plus this is for the fourth one. So similar is the case, higher order harmonics will come whole to the power of 1 by 2. This way only we will calculate the RMS value, it is already known. So when you simplify it, you will get it as 4Vm by pi root 2 into this form you will get it. So practically it is observed that out of these higher order harmonics, second order harmonic is the most dominant value here. Remaining components are very small fraction of the second order harmonic. So that's why this higher order harmonics can be neglected. Only second order harmonic can be taken as a ripple component. So with a little error. So that's why it will be IR will be equal to I2. That means second order component only 4Vm by pi root 2 into, I have taken only second order component out of this. 3 into square root of r square plus 2 omega L whole square. From this I can calculate the current ripple factor will be IR divided by I naught. So ripple component IR we have calculated here, I naught we have calculated above. So when you substitute and simplify, you will get your answer as 0.4715 times of R divided by R square plus 2 times of omega L whole square. So from this you can observe that as the value of L is increasing, automatically ripple factor is decreasing, or we can tell that the output ripples are removed as the value of the inductance is increased for a given value of R. In the same way, you can see that if the value of R is decreased, then automatically ripple content is decreased. That way also it is decreased for a given inductance. So the current ripple factor, this is 0.4715 into R divided by R square plus 2 omega L square. If R is far less than omega L, then this denominator can be simplified as simply 2 omega L. So this entire equation becomes 0.4715 into R divided by 2 omega L, because R is far less than omega L. So this will be 0.236 into R divided by omega L. 0.236 into R divided by omega L. From this we can tell the ripple factor is 0.236 into R by omega L, or this I can write as 0.236 into 1 divided by omega into tau, because tau is equal to L by R, time constant of this RL circuit, RL series circuit. This is already known. So we can tell that it depends on the time constant of your circuit. After adding the filter, if the time constant of your resultant circuit is more, so automatically current ripple factor is decreased, or your output current becomes more smooth. That's why the inductor filter is suitable for loads having very less value of the resistance or high load currents, whereas the capacitor filter, which is discussed in the last class, it is more suitable for the case of high resistance circuits. That means high resistance or low load current circuits, and this inductor is for vice versa. We have seen in the last class that in the capacitor filter also the current ripple factor is depending on inversely proportional to the time constant, because time constant for the case of capacitor filter will be equal to RC. Time constant is equal to RC. That means if R is more, time constant will be more, so it will filter more. That is the reason. You can please refer to last lecture. Another advantage of going for this inductor filter or filter is the transformer utilization factor improves, so by adding the inductor filter. But the disadvantage is your circuit becomes bulky and causes extra ohmic losses compared to the capacitor filter. In the case of capacitor filter, the losses are less and it is not bulky, it will be simple. Let us take one example to prove that what will happen if the resistance is less or more for a given value of inductor filter. So I am taking the example, single phase bridge rectifier has an input supply of 230 volts 50 Hz and load resistance R is equal to 100 ohms. Calculate the value of the inductance of L filter to be connected in series to limit the ripple factor to 5%. If this filter is connected to a load of R is equal to 20 ohms, let us assume for the same filter, if load resistance is decreased or the load is taking more current, what is the ripple factor? How much will be the ripple factor? So we know that the current ripple factor is 0.4715 into R divided by square root of R square plus 2 omega L whole square. Agree with me? So in this, it is told that the ripple factor should be limited to 5%. That means 0.05. Resistance is given as 100 ohms. So I have substituted here 0.4715 into 100 divided by denominator is 100 square plus 2 into 2 times of omega is 2 pi f, that is 2 pi into 50. L is unknown whole square whole to the power of 1 by 2. So if you simplify this, you will get your answer of L is 1.492 Henry. So the second part, it is asked for the same value of the L filter, if the resistance is decreased to 20 ohms, what will be the ripple content in the output? So again, ripple factor I am calculating 0.4715 into R is 20 divided by 20 square plus 2 into 2 pi into 50 into this L is this one 1.492 whole square whole to the power of 1 by 2. When I calculate it, I got as 0.01005, or this is nothing but 1.005%. You can see the ripple factor is so much decreased for a given filter if the resistance is less, or for a given inductance, lesser the value of the impedance of your load, the better will be the performance of your circuit. That is the advantage of this one. So now coming, you may get doubt, what will be the ripple content without any filter? So without any filter in this formula, you just substitute because filter not there. So L is equal to 0, substitute L is equal to 0 here. This will become R divided by R will cancel. You will get it as 0.4715. So we can tell without any filter, the current ripple factor is 47.15%. By adding this filter, you can see here the ripple factor is decreased drastically. In first case, it is decreased to 5% and second case, it is decreased to 1%. So this is the advantage of going for L filter. I hope the L filter is completely clear to you. So next class, we are going to discuss about the LC filter and then we will complete this converters topic. So if you still have any queries related to this topic, you can leave your comments in the comment section below. I will answer to your queries from there. Thank you. Thank you very much.